Okay, so what we need now is a nice way in which we can compare different distributions. Okay, so we test results. You want to compare your test results in different subjects. Well, how is it just a simple case of having a higher score makes it a better test result? Okay. Now, the first thing a lot of you guys do is you get your test result and then you compare it to the average of the class. So you're more worried about perhaps your ranking. Okay, in other words, how far up or down the list are you in terms of the class? Well, that's what our standard normal curve does. It turns everything into a distribution that has a mean of 0 and a standard deviation of 1. And so then your results become how many standard deviations above or below the mean you are. So my standard normal curve, there's our rule, if you like, is most importantly, my standard normal curve has a mean of 0 and a standard deviation of 1. Okay, which means then if I get a score of 1 on a standard normal curve, you're 1 standard deviation above. If I get a score of 2, I'm 2 standard deviations above. Similarly for -1 or -2. Okay, so it has all the same properties except the values along the horizontal axis, which we call Z values, refer to how many standard deviations above or below the mean we are. So things to note, it's a symmetrical graph, we know that. We know almost all the area lies within 3 standard deviations, which means Z is equal to 3 or -3. Mean, median, mode is all in the middle, which is at 0. They're the key things. And I guess if we want to convert a non-standard distribution into the standard normal distribution, the Z value that we find, okay, is just determined by subtracting your score. I got 56, minus the mean of the group divided by the standard deviation. And that compares your result to the how many standard deviations above or below you are. All right. So I guess in terms of practicalities, that's a key thing there. The Z value, X minus mu on sigma. All right. So let's have a look. This is sort of what we're talking about here. Well, in particular, we've got a normal random variable, mean 270, standard deviation 10. How many standard deviations away from the mean is the value X equals 256? So if we got a score of 256, how many standard deviations above or below are we? So my Z value is equal to my score. What was my score? 256 minus 270 over 10, which is equal to -14 on 10, which equals -1.4. So therefore, I'm 1.4 standard deviations below. So relative to the rest of the group, if you like, we've done really poorly. What about example 5 here? We've got 2 test results, one in math and one in physics. Which is a better result? In which test have we done better in? I know we've got a better mark in our physics test, but have we done better? So if we compare it to this, we get a Z score for it and see how many standard deviations we are above or below the mean. So my Z value is equal to 87 minus 78.5 on 3.9, which is equal to 2.17. So we've done quite well, 2.17 times above the average. Whereas in physics, my Z value is equal to 89 minus 85.3 over 3.2, which is equal to 1.16. So when you compare those two results here, 2 standard deviations above compared to 1 and a bit, my math results is a better result. Okay. I guess a more mundane usage of my Z value is to try and use that to help determine other probabilities. So again, as soon as I have a probability question, I'm going to draw a graph. Sorry, a normal question. I'm going to draw a graph. So what does this say? It says the probability that Z is greater than negative 2.1. It's less than 2.1 is 0.9821. So that's 2.1. So that makes all of that area there 0.9821. So that means the tail at the other end sorry, I'm just doing some calculations, lads. So that 0.0179 in that section there. Okay, so what does that mean? So the probability that Z is greater than negative 2.1. So where's negative 2.1? Negative 2.1 is there, which means the section there is the same as the section there. So the other area is just the same as that. Okay, so the chances of being greater than negative 2.1 is going to be the same value, 0.9821. The probability of greater than 2.1, well, we've just looked at that. 1 minus 0.9821, which is equal to 0.0179, less than negative 2.1, what's the same value, 0.0179. Between negative 2.1 and 2.1, which is that area there. So, well, we know all of this area here, if you like, is 0.9821, and I just want to subtract off that tail. So that's going to be equal to 0.9821 minus 0.0179. That gives 0.9642. Okay, so the key is to have a diagram, and then you use our symmetry values to try and determine the probabilities that we require. All right, on our CAS, I'll try and put a little snapshot in. The CAS is really nice. Again, we go to our key areas. We go to menu, probability, distributions, and you see the top one there is normal PDF, normal CDF. We'll stick with normal CDF. We always use our normal CDF here. So if I want to do this on the CAS, I'd have normal CDF. What do I want to go from? -1 to the upper bound of 2.5. The distribution type we have, the standard normal, so it's 0, 1. So if I just push enter on that, I'll get 0.8351. We'll keep it to 4 decimal places. If probability that Z is greater than 1, do exactly the same thing. So put it into the CAS. From 1 to infinity of all of that is 0.1587. This time around, if we've got a slightly different distribution, it's a 106 distribution. So we do exactly the same things. Go to menu, probability, distributions, number 2. Lower bound is 110. Upper bound is infinity, which is on our pi symbol. Except this time the mean is 100 and the standard deviation is 6. So I type that in and I get 0.0478%. between 90 and 110. So it's just really just basic calculator work. 110, 90.9044. This one here slightly different, a little bit of conditional. So remember our conditional laws. So that's the same as saying probability that x is less than 105 and between 90x to 110 over the probability that x, 90 is less than x, which is less than 110. So the top line, what numbers are less than 105 and in between 90 and 100? So, 90 and 110. So that's going to be the same as, well, 90 is my lowest value, but they've got to be less than 105. And the easiest way, I think, is just to guess some numbers. Guess a number and see if it satisfies that condition. If I pick 107, well, 107 is between 90 and 110, but it's not smaller than 105, so I pick some other ones. So on my calc, I'll just type it up. I'm going to have normal CDF 90, 105, 106 over normal CDF 90, 110, 106, and that will be equal to 0.8291. Righto. Okay, so what our inverse normal distribution tells us is we working back a little bit. If I've got a particular probability that I need to work out, if I need to know what value, how many standard deviations will give me a probability there of, say, 0.78, that's what I use the inverse normal for. Okay, so I go inverse norm. I've got a probability of 0.78. Which sort of a distribution am I going to use? So it might be a 0, 1, it could be 106, it could be anything. All right. So x is normally distributed mean, mu, standard deviation, 6, find. In this case, 0.95. Yeah. So really what I'm saying is I want to try and work out what value there will give me 0.95. Now, I know 95% lies within 2 standard deviations, so it's not going to be quite 2, but if I go to my CAS, we should be able to find an answer. This case is 1, so we'll go inverse norm 0.95, 106, which is equal to 109.87. Find C1 and C2 such that the probability between the two values is 0.95. All right, so what does that mean? So let's do my little table, little graph. C2, C1. So if that's 95% in there, that's got to be 2.5%, and that's got to be 2.5%. So that means the probability that x is less than C1 has got to be 0.025. Put that on my calc and I'll get an answer. And then that one there, well, if that's 0.025 there, if I subtract 1 from that, well, in fact, it's going to be symmetrical. If I subtract 1 from that, give me 1 minus 0.025, which is 0.025. 0.975. So using my CAS on both of those, I'll end up with inverse norm 0.025 106 gives me 88.24, which is about 11 and a bit, 11.7 below the mean. So now, if I want to know the probability that X is less than 0.975, that's going to give me 111.76, so 11.76 above the mean, which is what we were thinking we should get, something that's symmetrical. All right, what's the last one? Find the value of K says the probability that X is greater than K is 0.7. So again, if I just do a quick diagram here, that's 0.5. I need K here so that all of that is 0.7. The thing to remember here is that my inverse normal only gives the area below. Okay, so the inverse normal will only ever give us this section. So that means what I need is I need the probability that x1 or k, I suppose, and this is actually less than 0.3. So using the CAS, that'll give me. So let's have a look at this next example. This next example gets us to compare two different distributions, a standard normal with a distribution that has a mean and a standard deviation of 4 and 2. So there's my 4, there's 6, and we want to know, well, we're told the information we've got is that probability is less than 5. So for this curve here, the probability of being less than 5 is going to be given by normal CDF minus infinity to 5 of a 4-2 distribution, and that gives me 0.69146. And now I need to compare that. I need to know the probability that Z is less than what value is equal to 0.69146. So I now want to do the inverse norm, 0.69146 for a 0, 1, and that gives me 0.5. And that kind of makes a reasonable amount of sense. Let's have a look here. 5 here is half a standard deviation above the mean, isn't it? Because the standard deviation is 2, that's 1. So I guess my Z value, Z is equal to 5 minus 4 on 6, on 2, which is equal to a half. So the corresponding Z value is equal to a half, which is what we've got there. So in actual fact, it was a tech-free question that we could have done, but it certainly doesn't hurt us to practice working through with our calculator. All right, have a go at C.